Hello, everyone, and welcome back to a session of Math Made Easy. And in today's session, I want to start with parametric equations. Okay, so let's understand what we mean by that. Usually, parametric equations would be a very important tool in describing the motion, say, of a particle. So if you have a particle moving around a circle or some kind of a curve, how do we describe that? Okay. So in many problems that you will encounter, they will give you a parametric equation, and then you transform it into an algebraic equation or vice versa. We want to look at, if you are given a parametric equation, how do you plot it? Okay, so let's take a very simple example. I'm not going to tell you what shape that is. You should find it by yourself quite easily. So now we don't give you like an explicit equation, like we don't say y is a function of x, because in many cases we cannot describe it properly, right? Think about your conic sections. If I tell you, give me an equation of y as a function of x for an ellipse that has a semi-major axis value of 5 and a semi-minor of 3. It's awkward, right? Because x squared over 25 plus y squared over 9 equals 1, and you want to separate them, and then you want to find y as a square root. And then when you say square root, is it the positive or the negative? Because one of them will give you half the ellipse, the other will give you the other half. So do I need 1 or do I need 2, or should I write an equation? If x is greater than 0, use this equation. How? So it's awkward. Yeah, it's doable, but it's may not be quite easy and direct. So let's say I'm going to give you an equation, and I say, as I said, very simple one. X equals cosine of t, where t is the parameter. Usually you use the letter t, and don't ask me why. Mathematicians, unlike us mortal humans, they have their own thing. So you tell them, oh, x is perpendicular to y. They say, oh, you mean orthogonal? Okay, thank you. Anyway, we made enough fun of mathematicians, even though I have a channel for math, which doesn't make sense. Y equals sine of t. Like when you say, I had a student once I was tutoring, and we were always saying, this is the derivative of tan, like inverse tan. And when she wrote inverse tan in her test, she lost points because she should say arctan. Guys, be like real mathematicians. Don't say inverse tan or inverse sine. It's arc, right? So yeah, I had quite a few encounters like that, but okay. Look at those and tell me, how do I get a relationship between x and y? If x is cosine, y is sine. Yeah, some of you will say, okay, it's shifted by pi over 2, so maybe I can write an equation. But yeah, you can, but is it really, would that give you a relationship between x and y? Think identity trig. Huh? What do you know? Yes. Who said it? Didn't hear that. But anyway, we know that sine squared t plus cos, or I can write it cosine squared t plus sine squared t equals 1, right? That's a universal. Like we said, this is a special case of a more generic law that says if you have a line that makes angles of x1, x2, x3, x4, x sub n with hyperspace, like many coordinate axes that you can't even visualize or imagine, the sum square of the cosines equals 1. But when we are in the 2D case, cosine of the angle between the line and the y-axis is the sine of the angle between the line and the x-axis, right? So that's why we write it like that, as you know. Now, cosine square will be translated into x square, right? And sine square is y square equals 1. That's a unit circle. It's a circle of radius 1 that is in the xy plane. So if we draw, and of course, if I make that, for example, 2 and this is 2, then you get the radius would be 2. I make it 10 and 10, the radius is 10, and so on and so forth. So, but we are not yet done. Remember, I told you it's better describes the motion of a particle. So if I don't give you a limit on what is the value of t can be anything. It can go from negative infinity to plus infinity. So what does that describe? You would say, okay, let me make a small table. I'm going to write t, x, y. And I'm going to use the values of t that I know their sine and cosine. So for example, I start with a 0. I say cosine 0 is 1, sine 0 is 0, so I am here. Then I can pick a point. You know, if you use angles like 30, 45, 60, you are really getting square roots and stuff. Well, you still can look at it, but it's better to say pi over 2, because I know for pi over 2, cosine pi over 2 is 0 and sine pi over 2 is 1. I am at 0 and 1. It's telling me you are rotating in this direction, and you will keep going forever. Unless I tell you t, say, is greater than 0, less than 2 pi, in which case you will go just one cycle. What if I switch the sine and the cosine? Okay, so x would be 0, y would be 1. So I start here, and then I go still counterclockwise. And you can use a negative and stuff so to reverse the direction, but that's the idea. The idea is we are using trig most of the time to come up with an equation like that. Okay, x squared plus y squared equals 1. Let's take another simple one. Let's say I have the equation is, let's say x equals 4 sine t and y equals 2 cosine t. Notice there is no relationship between 4 sine and, however, I know if it's just sine and just cosine, I'm going to use the same approach. So let's rewrite it. Let's separate the sine of t, which is x over 4, and the cosine of t is y over 2. Then I'm going to square and add, because I know sine squared plus cosine squared equals 1. So I'm going to say, let's skip sine squared. So I'm going to say x squared over 16, which is 4 squared, plus y squared over 4 equals 1. Yes, that's the ellipse we were talking about. It has its center at the origin, and it's going to look something like that. This distance is 4. This distance is 2. But I don't know where I'm starting. And let's say t goes from 0 to 2 pi. Okay, so at t equals 0, x is 0. So I am here. But at t equals 0, cosine t is 1 times 2 is 2. So I am here. So here, let me write 0. 0 for the t value, okay, which is the angle in this case. Now, let's say pi over 2. So again, like we did before, 0 will give me 0 and 2. Pi over 2, since we are going from that, pi over 2, I see that x is 4 and y is 0, right? Because cosine. So 4 and 0. Huh, I am here. So now the rotation is clockwise, not counterclockwise. Okay, how about pi? I know already x is 0, but y would be -2. So I am here, pi, 3 pi over 2. This is -4 because sine of 3 pi over 2 is -1 times 4 is -4, and this is 0. So I am here at 3 pi over 2. And sure enough, if I say 2 pi is the same as 0, so this is 0 and 2 pi. So I make one clockwise rotation, or my particle has traveled one clockwise rotation about this ellipse. Now, let's take it one step further and make it more complete. It's still, I'm going to use the same thing, but now I'm going to tell you, let's look at new paper so we can refer to this one. I'm going to say, tell me how this particle is moving. So still x is 4 sine, but instead of t, I make it 2t or 3t, or I would change that, say, into 3t. And y equals 2 cosine, also 3t, and t is going from 0 to 2 pi. So I still have, whoops, horrible egg. I know this point is 0, 4 and 0, 0, 2, -4, 0, 0, and -2. And like before, I'm going to make a table, t, x, and y. T is 0 since I start at 0. So this is 0, and this is 2. Say, okay, it's the same thing. I'm starting here at t equals 0. That's identical. Yeah, but wait a second. I'm not going to jump to pi over 2. Why? Because if I say pi over 2, notice it's sine 3t. So I will be all of a sudden at 3 pi over 2. No, I don't want that. So let me say t is pi over 3. Why? Oh, in fact, pi over 6, I should say. Why pi over 6? Because when I multiply 3 by pi over 6, I get pi over 2, which I know the sine and the cosine. I just wanted to make it easy. Of course, I know the sine of pi over 4 and pi over 3 and pi over 6, but it's where is it? Like I will draw 30 degrees, 60 degrees, and the values would be roots and stuff. I don't care. It's just pi over 6 is good enough. I mean, you can do it, but it's a lot of work and it doesn't serve any purpose, right? Unless they tell you you're going from 0, say, to pi over 3. Anyway, let's look at that. So pi over 6 times 3 is pi over 2. Sine pi over 2 is 1. 4 times 1 is 4. Of course, cosine pi over 2 is 0. So like before, I am here. But notice, I reach that here at pi over 2. But this is 3 times smaller because I have 3 here. So I'm moving in this direction. And now I will be incrementing by pi over 6 every time, not pi over 2. So 2 pi over 6, meaning pi over 3, will give me 3 times that is pi. Sine pi is 0, but cosine pi is -1 times 2 is -2. So I am here at pi over 3. Then I'm going to add another pi over 6. So I get 3 pi over 6, which is pi over 2, we already know. Multiply it by 3, I get 3 pi over 2. Sine 3 pi over 2 is -1 times 4 is -4, and this is 0. So I am here at pi over 2. Notice, if I add another pi over 6, 1/2 plus 1/6 is 4/6 or 2/3, 2 pi over 3. When I multiply that by 3, I get 2 pi. 2 pi is like 0, so I will go back to this point, 0 and 2. So this is 2 pi over 3. I haven't yet finished and I'm back here. So I did one full turn and I'm still at 2 pi over 3. There is no reason to continue because it's the same pattern that would repeat. Next time you will add 2 pi over 3 to everything, right? So if I add 2 pi over 3, meaning 4 pi over 6 and pi over 6, so I will come here at 5 pi over 6. And then I will add pi over 6 to, so that would be, uh, oh, I'm sorry, did I add 2 pi over 3, which is 4 pi over 6, yes, and pi over 6. Here I add 2 pi over 3 to pi over 3, I get pi. And you keep going, and by the time you are done, you had made 3 turns because you make one turn in 2/3 pi, right? So in 4/3 pi, you will make 2 turns. In 6/3 pi's, which is 2 pi, you have made 3 turns. So 3 clockwise turns, and you end up where you started. So this at the end will be 2 pi. There is a 4 pi over 3 in the middle. So, oh, did you see now you can make the rotation clockwise or counterclockwise by switching the sine and the cosine. You can make it you can, if this was t over 2, for example, you would make half a turn. You will start here and end up here. So it's very flexible. You can change things. Okay, let's take another example. This time, let's say we'll make it a little more complicated. I hate the word complicated because it may scare you, even though nothing here is complicated so far, at least. So let's say this example, I'm going to say, oh, by the way, you can do that. You can plot these in your calculator easily so you see that what you did is right or wrong. Okay, so maybe we'll plot the next one. Another example, let's say, I want to make like something like a parabola. Or let's say x is, instead of sine, I make it sine square of t. And the y, I make it cosine t. Or let's say 2 or 3 cosine t. And again, t goes from 0 to 2 pi. Same concept. Sine square so far plus cosine square equals 1. I don't have cosine square, so I can say cosine of t equals y over 2. When I square that, it's x. When I square that, it's plus y square over 4 equals 1. Okay? So what is this equation? When I write it as x equals negative y squared over 4 plus 1, or 1 minus that, you can see that this is a parabola where its axis is the x-axis because that's not the squared one. And since that's a negative, it's opening to the left, doing like that. Okay, it can extend to infinity or not, we don't know. But you see how easy now we got that, a parabola. Again, t, x, y. When t is 0, sine 0 is 0, but cosine 0 is 1 and y is 2. So I am at point 0 and 2. In fact, let's just forget about that. So even if you don't know that this is a parabola, okay, and you have the x and the y. So you have the x and the y. you are starting here at 0 and 2. Now, how about when you make that pi over 2? Notice that I can have, they told me 0 to 2 pi, that another problem may tell you negative pi to pi or negative pi to 2 pi. It doesn't matter. They can give you whatever they want you to plot. So at pi over 2, this is x is 1 and y is 0. So I am here. 1 and 0 at pi over 2, and this is t equals 0. At pi, this is 0, and that's negative 1, so negative 2. So you are here at pi, which is 0 and negative 2. Then at 3 pi over 2, sine is negative 1, but you are squaring it, so you get x is 1. And cosine is 0, so you return back to where you were. So you see, and then at 2 pi, x is 0, and 2 pi is the same as 0, so you get 2. So basically, that's how we did. We started here. We went in this direction because the x was sine and the y cosine, so that's a clockwise rotation. If I switched, then it would have been a sine. So if I made that cosine square and this is sine, I would, well, it will change because I will start here. So I started here, went clockwise until I reached pi, and then I went back and ended up here. So I did turn clockwise and then counterclockwise when we reach pi, because the sine would have been negative and the cosine would be also negative in the third quadrant, but then positive in the fourth. So it's like you are going from the first quadrant to the fourth and then back to the first. That's a nice description. In fact, if I had not given you a limit on t, we would be going back and forth forever. So that's a motion along a parabola, a parabolic motion that goes back and forth indefinitely. Oh, I told you we are going to plot that. Well, here is the calculator. So where is, let me see the mode. Make that, yeah, that's a radian. So let's go and write the equation. So sine square t, there is a way. I'm going to write sine of t and then square the whole thing. And y is 2 cosine t. Now I need to know, I know already that the x goes from 0 to 1 and the y from negative 2 to 2. So when I go to window, I'm going to say t minimum is 0, t maximum is 2 pi. My x minimum is 0 and x maximum is 1. And this is negative 2 and 2, so I will leave that. That's the plot, but it doesn't show you how the particle is moving. But if you go to the table, you will see that, notice we started from 0, something, yeah, at 0 and 2. And then we went to pi over 2. You can go and say calculate a value when t was pi over 2. So it tells you x is 1, y is 0. And you can see that here. So you can trace if you want, but again, you can have the table, you can have specific values. and so on and so forth. But again, I think it's clear what happened here. Let's take maybe one or two more examples and we call it a day. Um, yeah, we did sine square and cosine. So let's say if I say x equals 3 cosine 2t, for example, so I make the x cosine back, and the y also would be cosine, but cosine square. So for example, 1 plus cosine square of 2t. Now I can no longer use sine square plus cosine square equals 1. So how am I going to do that? Wait, I have cosine 2t and cosine square 2t. So what is cosine 2t? Cosine 2t is x over 3. So let me substitute that here. So I say y equals 1 plus x squared over 9. Wow, that's almost identical to this, right? It's a parabola, but now it's opening up because y is the axis of symmetry, and this is positive, so it's opening up. So it's going to look something like that. But I don't know how the particle is moving, really. So what I would like to do is to give what is t. So let's say t, again, we can write that t goes from 0 to 2 pi, or from, it's 2t, so we can make it 0 to pi. Do you see why? Remember when we did 3t and we ended up with 3 rotations? So let's make that 0 to pi. And we are going to assume we don't know the shape, or how we know the shape, but we don't know how where the particle is starting, where it's ending, how it's going to move. So here is the x, here is the y, and the t. We are going to find it with these calculations. So when t is 0, cosine 0 is 1 times 3 is 3, and cosine is, I'm sorry, I said cosine is 1. Cosine 0 is 1 times 3 is 3. Cosine 0 is 1. Square is also 1, plus 1 is 2. So I start at 3 and 2. And here t is 0. Notice it's 2t, so I'm going to say pi over 4, because when I multiply it by 2, it would be cosine cosine pi over 2, which is 0 times 3 is 0, but this is 0 squared plus 1 is 1. So I end up with 0 and 1. So I am here. And then at pi over 2. Pi over 2, that would be pi. Cosine pi is negative 1 times 3 is negative 3. And sure enough, here cosine pi is negative 1, but I square it and add, so it's negative 3 and 2. Okay, so my particle is moving along this thing, this parabola, but it's opening up. And I'm here at pi over 4, here at pi over 2. Let's see what happens at 3 pi over 4. When I multiply it by 2, I get 3 pi over 2. Cosine 3 pi over 2 is 0. And cosine 3 is 0 plus 1, 0 and 1. So I return back to this point at 3 pi over 4. And sure enough, I will end up here at pi, because cosine 2 pi is 0, so I get back to 3 and 2. So my particle started here. It's like when you have a trough and you have maybe some kind of a small ball, you place it here, it goes up here and then back. Usually it doesn't go to the same height due to friction, but if we don't have friction, it will go back and you hold it. Okay, you pick it up. If you don't make a restriction, so this thing would go back and forth forever, like a pendulum. Okay. Again, you can plot that with a calculator. Finally, let's take, because all of the problems so far I gave you were having like sine and cosine. So let's take something different. And that's enough. I mean, if you take a more advanced course in math, you will get two cases where you have a helix or other stuff. It's not hard. You're just going to plot some points and connect them. It's really that simple. So let's say if I tell you x is secant t and y is tan t. Oh. And t, notice here t cannot go from 0 to 2 pi. Why? Secant is 1 over cosine, so I cannot reach pi over 2 or else I will go to infinity, right? 1 over 0. Same thing here. I cannot go to pi over 2 or negative pi over 2 because tan t would be either plus infinity or negative. In fact, it's undefined exactly at pi over 2. So what do? We can say t is greater than negative pi over 2, less than pi over 2. So you don't touch the pi over 2. You go very close to that. Okay? So let's see. What do I know? I know that sine square plus cosine square equals 1. You don't have to memorize anything else, right? If you say sine square t plus cosine square t equals 1, you want tan. Tan meaning sine over cosine. So let's divide everything by cosine square t. Cosine square t. Cosine square t. This becomes tan square t, the y square, plus 1 equals 1 over cosine is secant. You get secant square t. So basically, I'm saying y square plus 1 equals x square. Usually we write it y square, I'm sorry, x square minus y square equals 1 when I subtract y square from both sides. So I have the variables on one side and the constant on the other. What is that? It's a hyperbola. And it's a hyperbola that has its longitudinal axis is the x-axis. So it's opening right and left. And here is the origin. But I still don't know how my particle would work. So we say t, I'm going to write negative pi over 2, but it's not negative pi over 2, just slightly higher than that. What is x? What is y? If it's negative pi over 2, I know that cosine pi over 2 is 0. I'm dividing by 0, but it's slightly be careful here. Because if I am at negative pi over 2, slightly before negative pi over 2, I'm in the fourth quadrant. And the cosine is positive, not negative. So secant would be a very high value approaching infinity. But what about the y? The y would be approaching negative infinity. So the x is approaching positive infinity and the y negative infinity. I'm somewhere here, very at the bottom here. This is t is negative pi over 2. How about negative pi over 4. Negative pi over 4, my cosine is in the fourth quadrant, so it's positive, and its value is root 2 over 2. Secant is the reciprocal, so it's 2 over root 2. Square it becomes 4 over 2 or 2. My y, on the other hand, is negative. It's negative 1, right? Oh, I'm sorry. I was substituting. I was substituting in those. Oh my God. I'm sorry. Um, so let's go back. When I say negative pi over 2, slightly before negative pi, we are in the fourth quadrant. So pi is, I'm sorry, the cosine is approaching 0. So the secant is going to plus infinity. Then that would be, we said it's almost negative infinity. So we are here. At negative pi over 4, um, I should have picked. Okay, so at negative pi over 4, it's 45 degrees. So this is root 2 over 2. I was squaring, I'm sorry. It's because, but this is my equation. I substitute here. So secant would be square root of 2, which is the reciprocal of cosine pi over negative pi over 2. But the tan of negative pi over 2 is negative 1. So I am at root 2 and negative 1 somewhere here. X equals 1. So this is negative pi over 4. How about 0? Secant 0, cosine 0 is 1, and secant is reciprocal, so it's also 1. The tan of 0 is 0. So I am at 1 and 0 here. This is negative pi over 2. How about pi over 4? The cosine is still negative 2, but now the y is 1. So I will be above this point here at negative pi over 4. At pi over 2, not exactly pi over 2, but not exactly pi over 2. This is 0. 1 over 0 is infinity, but 10 is also going to infinity. So really, I'm starting from the whole branch, right? Going to infinity. I didn't use the left branch. The left branch, maybe from 0 to pi, we don't know. So if that tells you t is from negative pi over 2 to pi over 2, comma, say pi over 2 to 2 pi, or 2 pi, meaning what if you continue? We haven't done that here, but maybe you can try. If you start with pi, x would be negative, so you go to the other branch. So maybe the particle is going like that, and then all of a sudden it appears like some games, you see the particle is moving to the right of the screen, and then it comes back from the left or something like that. So we can play with these things, and the idea is that you know your trig identities, and most of these problems, the trig identities would help you figure out what is the rectangular uh, equation, and then you plot it and you get. So we knew from here that it's going to be a hyperbola, but is it two branches or a single branch? Does it go all the way from negative infinity to infinity, or does it start at 0 and stop somewhere? That all depends on the limit on the t parameter they give you. I think it's too long what we covered, so I will stop here. And again, if there is anything that was unclear, please don't hesitate to comment, and I will get back to you as soon as I can. Thanks for your time and have a great day. Bye. Oops.